So I think one thing that's really important for you to understand is that action potential, it is the nerve impulse itself. It is that electrical impulse that we get, which will get delivered to the central nervous system, then to the motor neurons, then to the effector, which generates like an actual response. So if I was to give you like an example, by the way, I'm talking about this right now because previously I did not actually know what an actual potential is. So now I'm going to give you an example. So let's say my point just now was that action potential, it is the electrical impulse that we talk about every day. And bear in mind, there's one thing that's really important is that not everything that your body physically feels will become an impulse. What I mean by that is, so let me give you an example. So you have skin, right? Let's say this is your arm, and you have hairs on your skin. You have like a lot of hair on your skin. This is arm. And since these hairs, they're tiny, so literally every second, every moment, there will be some wind or like temperature that's maybe affecting this hair. So maybe it kind of like deviates. It does not just like stay stationary, it kind of moves. It could move, it could bend. There's many possibilities to what could happen. However, you don't really feel what goes on with these skin hairs unless let's say there's like a great wind and you feel all your hair like get cooled down because of it. If you are feeling if you're feeling that your skin is cooling down because of the wind, that is when we actually have created an electrical impulse. This is why I say not every stimulus will create an impulse. Only the ones that are beyond a certain threshold will create this impulse. And what is this threshold I'm saying? So this is the second thing I'm going to talk about, the threshold potential. This is negative 50 millivolts, and I'll talk about the value later, but basically it is a minimum potential you will need for an action potential, i.e. the electrical impulse, to be generated. Impulse. This basically means that okay, let's say now I'm burning your finger. Let's say you're touching like a hot source. If this source is not hot enough for you to feel any pain, that's when um like the signal created isn't above the threshold potential yet. So that's what we mean by the threshold potential. So if the stimulation results in a depolarization that's less than 50 millivolts, there's no action potential. Therefore, there's no response generated. And even though you might be touching something that's slightly hot, you will not feel that it's hot. You don't feel a thing. And if the depolarization is equal to or above 50 millivolts, this is when you have an action potential. And yeah, the size of your action potential will be above 30 millivolts and it's fixed. This relates to our all or nothing law, which I'll come back a bit slightly later because I'll need to talk about the graph. This is membrane potential against T. This one is membrane potential. and this is T right here. The graph has a shape that is something like this, and I'll talk about it later. But there's a thing that I wasn't really clear for a long time. That is, before the action potential was about to be generated in the first place. So this is basically how the action potential is generated. A process like this happens, these kind of things happen for us to create an action potential. But what happens before that? Since I know that the action potential is generated inside the sensory neuron, but I don't really know what goes on before the sensory neuron. So if you check my wrong app. If you check my my message with DeepSeek, that's actually my confusion. So my confusion was, let me try to find it. So I was confused what happens before all the influx and efflux of Na plus and K plus happen. Like what actually happens before that. Now I know there's something called the taste chemoreceptor cells, and this actually highlights what goes on with the stimulus and the receptor, and how the receptor actually tells the sensory neuron to create the action potential. So this is what I'm gonna talk about like right now. So if you know about homeostasis, you know that basically how we respond to a change is that you have a stimulus that could be light, heat, sound, a lot of stuff. Basically something that's different and something that might be harmful for us that we want to avoid. So basically a stimulus. A stimulus is going to be detected by a receptor. This receptor will send this message. No, there's no message as of yet. But receptor will carry this change to the sensory neuron, which get delivered to the relay neuron, kind of running out of space. And then it goes on to the motor neuron. Sorry, the drawing disappeared. And then it will go on to the effector. The effector could be like a muscle, could be anything that actually carry out the change. The change meaning like a response. So maybe like if you're touching something hot, your response will be to move your finger or whatever you're touching the hot stuff with. So let's start from the very beginning. And we're gonna create a scenario here. So my scenario will be you're eating something that's salty. So if it's salty, it contains salt in it. And salt basically is sodium chloride, contains Na plus and Cl minus. So if you're eating something hot, if you're eating something that's salty, the salt and specifically the Na plus ions, but right now they're in your mouth right now, the food is in your mouth, and the Na plus ions from food, actually just let me write down the actual thing. From food is going to diffuse into your cell. The taste is gonna diffuse into the taste chemoreceptor cell, while the microvilli, which is on the cell. Basically, the cell looks something like this. That's the nuclei, and these are the macrovilli. And this increase in the sodium ions is going to result in an increase in positive charge inside the cell. So inside this cell, because of the Na+, inside the cell will become more positive than before. And since there has been a change in the charge difference between the inside of the cell and outside of the cell, we say this membrane has become depolarized. And this actually generates a receptor potential. You can kind of think of it as the change in potential difference across this membrane. So before, let's say this membrane, like this is your cell, this is the outside, this is your inside. Originally, there will be no charge difference between here and here, but now between here and here, we can say that here is more positive and here is more negative. So there has been a change in the potential difference across the membrane of the taste receptor cell. Okay. So due to this receptor potential, the voltage gated calcium channel will open. So calcium channel will enter the cell. I'll talk about this part later because this is related to the synapse. So the influx of calcium ion is going to trigger the movements of vesicles containing neurotransmitters. And these neurotransmitters will be released. And let me just draw how it looks like right now. Remember, we have our taste chemoreceptor cell here. And actually down here, for the same cell, we can call this a presynaptic membrane, because later you'll realize this is actually a synapse process. And this part is the dendrite of a sensory neuron. Now we also call this a post-synaptic membrane. So make sure you understand this part. So this is a taste chemoreceptor cell. This is part of the sensory neuron. This is the dendrite of the sensory neuron, which basically down here you have your massive cell body, and then this is the nucleus, and then later on this is the axon, and this is where the action potential will be generated and passed on. So the neurotransmitters, they will stimulate the action potential. This will be covered in detail later on in the sensory neuron. And that will send the impulse to the taste center in the brain. That's like an overall rundown of from stimulus to the CNS. Okay, so I hope you understand this part, and I'm going to quickly look at my confusions before I understood this part. So one thing that it did not really understand is that I was confused that in the step 4, it is said that the entrance of calcium 2 plus ion into cell would trigger the movement of vesicles containing neurotransmitters. So I think my confusion was, is it the neurotransmitters that cause the ligand-gated sodium ions channels to open, or was it the receptor potential that causes the ligand-gated sodium channels to open? So the real answer is the thing that actually causes the ligand-gated sodium channels to open was the neurotransmitters, not the receptor potential. Remember, the receptor potential is something that was set out only across the membrane of the taste chemoreceptor cell. So the receptor potential is only like across this membrane, and there's nowhere to be found after that, because later on Ca2 plus will be like released into the cell, which will then simulate the neurotransmitters to be released. So the receptor potential is only like part of the process. It only stimulates the production of, no, not the production. It only stimulates calcium 2 plus channels to open. That's its only job. So maybe I'll draw like an arrow between those two things. This is the cause, and this is the effect. Okay, so for you to fully understand this process, I'll have to talk just briefly about how the synapse works. So this is the structure of a synapse. So if you remember what I talked about just now, I talked about the influx, not the influx, so let's say I draw like a taste chemoreceptor cell right here. As the sodium ions flow in, I have created a membrane potential difference. So basically maybe here you'll get like more positive, out there you'll be more negative. So I have set up a difference between the membrane. So I have generated a receptor potential, and this receptor potential, it will cause the voltage gated Ca2 plus channels to open, and Ca2 plus is going to enter the cell. Ca2 plus, they will enter this cell, and this Ca2 plus is going to stimulate the production of those neurotransmitters. Not the production. They will stimulate the movement of the vesicles containing neurotransmitters to move to the presynaptic membrane, this membrane over here. And you see those neurotransmitters, they're neurotransmitters. They're going to bind with a receptor on the postsynaptic membrane, and this postsynaptic membrane, for our scenario right here, this is actually already the sensory neuron, part of sensory neuron, not neutron, neuron. And if you want to know like a bit of detail, this is actually the dendrite that we're looking at. So this neurotransmitter is actually not going to it's going to bind to the receptor on this surface. And what actually happens, wait, I'm flipping the pages of my book right now because I kind of forgot what happened. Okay, so these receptors, these are receptors for neurotransmitters. They are going to undergo a conformational change, actually. Conformational change. And this conformational change is going to open the ligand-gated sodium channels. So let's say I'm going to draw like two here really quickly. Let's say this is the ligand-gated. Maybe it's not located here, but now I'm just trying to demonstrate the idea of it. This is the ligand-gated sodium channels. By the conformational change of the receptors right here, the ligand-gated sodium channels, they're going to open. So imagine, let me redraw this. Imagine before it's like a closed box. Now it's going to open. Open would look something like this. It's going to be open both sides. It's like a switch. And obviously the sodium ions can then like go into the sensory neuron. And this is actually what happens. So let me see if I've mentioned it just now. It is not here, it's actually later on in this part. So I'm not sure if you understood the part just now, but that perfectly connects to how our action potential is being generated. So now, if you look back at my drawing just now, you see the ligand-gated sodium channels will open because of the change in conformational change in the receptor due to the binding of the neurotransmitters. Remember this part? I'm now going back to my original page. This is a page that is going to explain to you how is action potential generated. So you can imagine this as the second part of the video. Okay. I'm just going to go through my notes. Neuron is typically stimulated at the dendrites, and electrical impulse will spread through the cell body. Well, what is the electrical signal that we're talking about? I'm going to go back to DeepSeek. And now, it said that the electrical signals in dendrites, they came from the neurotransmitter binding. So, going back to our notes, if you remember just now, neurotransmitters have binded to like the dendrites, the postsynaptic membrane on the dendrites. This causes an electric signal that results in the opening of the ligand-gated sodium channels that we're talking about just now. I'll label it using the same color so you know I've talked about it just now. And this obviously allows Na plus ions to flow into the cell. So now, the Na plus ions will flow into the cell, and this is originally I'll draw like an original version of the across the membrane of a cell. So there's something called the resting potential. Actually, I don't have to draw one. The resting potential is when your body or your senses isn't sensing anything that's like extremely different or different from your norm. So basically, when your body is not in touch of anything, that is your resting potential. So my resting potential, if I'm talking about temperature here, is maybe when my finger is not touching something extremely hot for my finger to handle. So that's my resting potential. It is basically the state when you have no stimulus whatsoever, and the resting potential has a voltage of negative 70 millivolts. So this is basically the norm of across your membrane. Across your membrane, I mean like, so this part onwards of the membrane, this part of the membrane. What I meant by in is this is inside the dendrite, or inside the sensory neuron. This it's outside sensory neuron. And basically this is how like the original setup looks like. We actually have a negative membrane potential, which means that inside the membrane, inside the sensory neuron, we have a much negative potential than the outside. That's basically what I mean by the negative right here. And now if I consider that, now remember originally it is more negative out here than negative inside the sensory neuron than the outside of the sensory neuron. And the difference in the voltage is negative 70 millivolts. But now I'm actually pumping some positive charges, the Na plus, into the cell, into the sensory neuron. So that makes my inside of the cell a lot more positive, and my negative charge is going to decrease. It'll become more positive, and the outside of the membrane will become more negative, so the positive charge also decrease. So this means that since I'm considering like the charge of the inside of the sensory neuron, as the charge of the inside becomes less negative, my value for the membrane potential will also become less negative. So you see this graph, it's becoming less negative. This is due to the sodium ion influx. So the influx of sodium ions from the ligand-gated channel is going to create a current, and this current is going to travel towards the axon hillock, basically like the end of the axon, like this part, that's the axon hillock. Okay, if the Na plus keeps flowing into the sensory neuron, and the electrical impulse eventually reaches above the threshold, which is larger than negative 55 millivolts, the action potential will be generated at the axon hillock, which will travel down the axon. So later on, a very important thing will come into play. It's called the voltage-gated ion channels. So let me just introduce you to the voltage-gated ion channels. So they're regulated by the membrane voltage. So basically the difference between the potential difference across the membrane, like inside the outside, the difference between them. So the channels, they're really picky. They only open at some of the membrane potentials, and they're closed at the others. And we have two types of voltage-gated channels. One is sodium plus channels, and one is K plus channels. And bear in mind, the minimum voltage for me to open my sodium and potassium voltage-gated ion channels is negative 55 millivolts, or negative 50, according to my textbook. So now let's go down. If my membrane potential has reached the negative 55 millivolts, so this is when I have, like, remember at the resting potential, my membrane, the outside was quite positive, right? Quite positive, and the inside was quite negative. Well, now what's happening is that inside my membrane, since there's more positive Na plus, due to the influx through the ligand-gated sodium channel, now my negative charge inside the membrane actually decreases, and the positive charge outside the membrane is also going to decrease. So basically our potential difference is getting smaller, closer to zero, and this is essentially what happens. Well, since negative 55 is definitely closer to zero than negative 70. Okay. So the Na plus rushes into the cell. They did. By the way, I had to draw like imagine this is my sodium channel, ligand-gated sodium channel. Because the Na plus flowed in, there's more positive charge inside the sensory neuron, and the cell membrane is further depolarized. And this allows even more sodium channels to open. This is a positive feedback mechanism. So this positive feedback continues until all these sodium channels are open, and this corresponds with the rising phase of the action potential. This part, you see this part? Because there's more sodium channels that are opened, so I'm going to open them up. Let me draw it again. Oh, by the way, this is not the ligand-gated this is not the ligand-gated channel, sodium channel anymore. This is a voltage-gated. And because of the positive feedback. Now I have more sodium channels are open, so there's even more sodium ions inside the membrane. And the inside of membrane, eventually it becomes so positive that the potential difference between them, like across the membrane, actually reaches to the positive. You see, plus 30, that's actually like a positive potential difference. And one thing I didn't talk about just now is that I told you that the Na plus channel, voltage gated channels open. They open really quickly. There's another channel that opens as well. That's the potassium voltage gated channels. But they open much slowly than the sodium channels. So that's why with this happening, there's actually also K plus that's slowly going out of the membrane. Slowly. Much slower because not all of the K plus channels are open yet. And this is what is happening. After all the Na plus channels are open, eventually we reach to this peak. And when we're at this peak, the Na plus channels will begin to close. And by this time, the K plus channels are fully open. The K plus will rush out of the cell, and the voltage will return to its original resting value. So this is my original. Originally, there's less K plus outside than inside, more Na plus outside than inside. That's why the K plus moves out of the cell, while the Na minus moves inside the cell. So now there's more K plus, less Na plus, more Na plus, less K plus. There's something that's quite funny. So as the K plus channels, they are quite slow to close. The K plus, they're going to leak across the membrane. So that's why the membrane will actually become more negative than it used to be. This is what we call as hyperpolarization.